Okay, so last time we talked about generalized linear mixed models, and we talked about a common way to fit these models. If you set up the likelihood, then you have a complex likelihood, but you can use what's called Gaussian quadrature to fit the model, to optimize it and get your parameter estimates. And so that gives us a way to fit a generalized linear mixed model. There's some downsides to it though. And one being that we don't have a good way to deal with serial correlation, because we can add random effects. So we can add a random intercept. We could add, even like a random intercept plus a random slope for time, things like that. But we don't have a good way to add like the AR1 structure to those kind of models. And the reason is because for the basic generalized linear mixed model, there's not an error term, right? Any generalized linear model or generalized linear mixed model, we link the mean of the distribution to the linear predictor directly. And so there's no error term in the model. And so we can add in a nutshell, you can add random effects, but you can't add an error covariance structure to deal with repeated measures. So it does give us a way to deal with correlated data, but it's more limited than what we were used to with the linear mixed model, right? Because for the LMM, we can do both. We can add random effects, and we know that that's one way to deal with repeated measures. And we can specify the error covariance structure, and that gives us a lot of flexibility in dealing with serial correlation. So are you familiar with the term serial correlation? So serial as in SERIAL, as opposed to the cereal that I just ate this morning. Have you guys used that, or did Gary bring that term up? So serial correlation is like the day-to-day correlation that goes on for a long period of time. That so there's a pattern, I guess you could say, to the correlation. And with the AR1, the correlation between today and yesterday is going to be higher than today and a week ago. And so there's a natural decay in the correlation. That's going to happen for a lot of longitudinal data. And if it's going day to day to day to day, then we call that serial correlation. So really, we'd like to find a way to have this generalized linear mixed model, but also be able to adjust for serial correlation as well as add random effects. Okay, so that's what we're going to talk about how we can do today. What I have on the screen right now, this is actually just a follow-up to some of the questions that came up last time. And I after the lecture last time, I watched the full lecture. You might be thinking, wow, you must have been really bored. Why would you watch the whole thing? I don't know. It was weird. I just wanted to see what it looked like. And as I watched it, some of the questions that came up, I think I answered okay, but there were a couple that I went back and kind of looked at, and then a few that I listened to, and I was like, wait, I didn't hear that question exactly right. Sometimes when you're teaching, you kind of think you've heard the question, but I didn't really, until I went back and listened to it. There's one or two that I realized the question was different than what I answered. So so the first one, I talked about a fair amount. I don't want to spend a ton more time on this, but the PARM statement in proc-NL mixed, those give you starting values essentially for parameters, and it could be It could be fixed effects or covariance parameters. So any parameters in your model, you can specify starting values, which should help the numerical algorithm go to the correct solution. So the closer you can get on the starting values, the better. Now, why do you need to worry about this? Because I mentioned, you know, you could use starting values. Some procedures use starting values like using a naive method, which is pretty good for to get starting values. So for example, for a generalized linear mixed model, we could use the regular generalized linear model to get starting values, and that's what proc limix usually does. But proc NL mixed just uses 1. It says, okay, I'm going to use 1 as starting value for all your parameters, and that's pretty, you know, that could be pretty far off. And that's the reason why, for the data set that I showed you, I did my own, you know, initial fit, and it could just be, you know, ignore the correlation. What do you get for the initial values? So you could run a proc gen mod or something like that to get initial values. But NL mix was made to be a very generic. It's a very generic procedure, and that way you can really build things on your own, right? So it's not going to use any canned mechanisms. You really need to specify things. So if you want to use better starting values than 1, which you probably can get, then you can figure out what those starting values should be. They don't need to be perfect, but just in the area, so that when the numerical algorithm works, it's starting from something that's closer to the solution than 1. You know, that we'd expect that to be, you know, probably not good starting values in general. So that's that point. The second one was a good question. I think Jonathan asked this one about inference for fixed effects. So despite the fact that the outcomes are non-normal, so we have binary outcomes, we have count outcomes, things like that, the distribution for the fixed effects estimators are approximately normal. So the beta hats is what we're talking about. Those are approximately normal, and the more data you have, the better that approximation is going to be, right? Because of what theorem tells us that's going to be the case. This will be an audio chip. That's right, CLT, central limit theorem. Right, so if we have, even if the distribution, you know, of our beta hats are not, or if we're dealing not normal, or if we're dealing with non-normal outcomes, which might put that in question as well. We know if we have a larger sample size, that distribution for those estimators, you know, as the sample size increases, is going to become more normal. Okay, but one of the key things is I want to distinguish the outcome from the parameter estimators, the fixed effect estimators. Just because you have a binary outcome doesn't mean that your beta hats, that's different. That's a different distribution. So despite the fact outcomes can be non-normal, the estimators of fixed effect parameters themselves are approximately normal, which becomes more true, especially as sample size increases. So we're going to use t-tests and z-tests. What's the difference between the t-test and z-test? Well, the t-test, as I mentioned here, if you don't know the covariance parameters and you're estimating them, you want to account for that extra variability, right? And that's what we do in a t-test. The t-test, or the t-distribution, has more area in the tails relative to the standard normal. And it's because we use the sample standard deviation in place of the unknown population standard deviation. That's for a simple test. It's the same principle here, right? But it's just that we have more covariance parameters that are involved. Oh, so here's a good one. Benjamin asked this question, and this is one of the ones where I thought I listened to what he asked, and I didn't, when I went back, I was like, wait a second, he's asking something a little bit different. He was asking if you have an odds ratio, and you want to put that in a statement, do you need to say average like you do for slopes? Like we know that, if a slope is 2, you want to say, the average increase in the outcome per unit increase in X is this. And if you don't say it, you're saying you're just saying the increase is 2. You're kind of implying that's the case for everybody. But if you have an odds ratio, typically you don't say average, okay? Because the odds ratio has the statistic embedded in that word. So you can say estimated odds ratio, or something like that, or the estimated odds increase by a certain amount. For an increase, for 1 unit increase in X or something like that. So so typically it's okay just to say odds. So again, the odds encapsulates the statistic when you say that. Here's a good question. In a nutshell, see if you guys know this now. If you don't, then I'll just stick it on homework. And it's not that hard. It's something that you can think about. But if anybody can answer it now, then I won't stick it on a homework. So that maybe motivates you to, see if you can do it. In a nutshell, why is the likelihood more complicated for non-normal outcomes than normal outcomes? Can you give me two or maybe even one sentence response based on what we learned last time? So think about the likelihood. Think about the likelihood for the linear mixed model, and think about the likelihood for the generalized linear mixed model.
Is it because there isn't a closed form solution for the generalized likelihood?
That is right. That's a correct answer. But if I were to ask you for more detail and explain what you mean by that,
You'd have to employ numerical methods to get to the likelihood.
Yeah, and that's because it's complex, right? But what makes it complex? What specifically makes it complex?
Just the link function?
Yeah, I mean, that kind of is in the area of the right answer. But again, I'm looking for something a little more specific. So if you can think back to last time and think about how we set up the likelihood, what is the thing that we had to employ to get the right PDF in the likelihood?
Is it because you have to calculate the total probability?
Okay, you're getting closer. You're getting closer.
Oh, is it because you have to integrate the total probability pieces by small pieces?
Okay,
So you have to
that's
do like
That's
asymptotics?
pretty much it. Yeah, that's pretty much it. So we couldn't just write the density of the outcome like we can for the linear mixed model. To get that density, we had to express it using the theorem on total probabilities, right? So we had the conditional density times the density of the random effects. And we had to integrate over that. That would give us the density of Y, but we can't get that in closed form, right? So so you basically answered it. I feel like what I still would maybe ask this question on homework, just so that you can think about it and write it in a nice couple sentences. So that'll be on the homework. Pretty short thing. It's not going to be a hard question. And then I should have this homework posted within a day or two. And I'm going to give you a couple weeks on this, because again, I want you to, for those people that have projects where you have count data or binary data, this will be useful, you know, to kind of get some practice with these types of outcomes. But I do want you to have time. I want to space things out so you don't get burdened by having a homework and having to set your project aside. I kind of want you to be able to have time to continuously work on that. And then we'll see about whether or not we'll have a homework after that or not. Okay, I will at least post another homework. Whether I collect it, I'm not sure yet. Maybe a short one or something. So one other comment I wanted to make, the last comment here is, I know that sometimes I jump through slides, and that's not to say don't worry about the slides at all. Please make sure that you go back and read through the detail, because it is important. We only have so much time to spend in this lecture, and I don't always want to get bogged down in detail. I want to be able to get the main point across, and I want to be able to have discussion. I think it's important to use that time in lecture. So this is just a comment that, you know, please make sure you read through, especially as you're getting prepared for a quiz or something like that. So that's that. Any other questions before we start marching forward with the new slide set? I want to see you guys. There you are. I may go back to speaker view here in a second, but I want to make sure I see you guys. All right. So let me get out of there.
We still have a quiz Monday, right?
Is it Monday? Is it this coming Monday? Should have stayed in there.
Did I make that up?
I don't know.
I could be wrong.
Does somebody have, I just logged out, so does somebody have that calendar that I made up and put on the, or I could take a look at it again if it's.
Oh, the 9th. I have it written down as
Is it the 9th? That's okay. So we have next week, a couple lectures next week. You just gave everyone a good scare there.
Sorry.
Yeah, no, that's okay. So we have next week, and then we have a quiz the following Monday. I think probably what I'm going to do is next week, next Monday, there'll be some material, and then Wednesday maybe part of it, and then I'll spend some time in review next Wednesday, a week from today, so that you guys have a good sense of what to prepare for that second quiz. All right. Get everything set up here. So we're still on the topic of generalized linear mixed models. And we're going to talk about an alternative way to fit a model other than the quadrature approach that we used before. So sorry, I'm still playing around with the. Okay, sorry. So we're going to talk about an alternative way to fit a generalized linear mixed model. And like I mentioned last time, this is my favorite way to do it. You know, if you can, we basically have three methods. We have three methods. And so when we're dealing with non-normal data, and it's also longitudinal. There's three ways we can deal with that. So we have these three approaches. The first that we learned was GEE, right? And the second way was to define a generalized linear mixed model and use quadrature. And in this case, you're approximating a true likelihood. And we're going to learn today about how to fit a generalized linear mixed model using the linearization approach. And we also call this pseudo likelihood. So now we have another word. You know, the wording in statistics is really kind of, it can be confusing. It's kind of generic and confusing sometimes. So we have all kinds of likelihoods that we've learned, right? So we have, for likelihoods, this is kind of an aside, but it kind of relates. There's different types of likelihoods that we've dealt with, right? We dealt with the regular, the standard, I should say, I'll just say standard. Pen, sorry. Go away. Somehow I'm in the header. That's what the problem is. So let me get out here. Okay, so we have the, I'll call it the standard likelihood. We have the restricted or residual. Okay, we also learned about a profiled likelihood, which is really a different way to express the standard likelihood. Then we learned about quasi-likelihood. Where you don't need to specify, well, there's a couple ways you can look at it. If we add a dispersion parameter, we're dealing with quasi-likelihood. Or if we don't need to specify the whole distribution, but just the mean variance relationship, like we did for GEE, then we have quasi-likelihood. And then what we're going to learn about today is pseudo-likelihood. So what does pseudo mean? It means sort of, right? What does quasi mean? It means sort of. So we're using all these different terminology that it's kind of vague, and it becomes really complicated when you start reading the literature, because different people will say different things. For example, we're talking about pseudo likelihood methods today. In other initial papers, they actually called it quasi likelihood, which makes it confusing because we want to distinguish what we're learning today from you know, the quasi likelihood that use like for GEE. So the terminology can be confusing, and there's a lot of different variations that we need to learn in class. So I'm going to use, you know, define terminology in very specific ways to try to avoid that issue. So why do we call it pseudo likelihood? We'll talk about it in a second, but basically using this linearization, what we're going to do is we're going to take any type of outcome. It could be binary or count or something like that. And we're going to transform it so that it's approximately normal, and so that we can employ linear mixed models. And that way we can utilize what we have. I feel like I'm talking way over here. I need to look at you better. Let me move this a little closer. Okay, sorry.
Matt, are you showing any slides?
Yeah, did it stop sharing?
Oh, yeah, I still see the follow-up remarks doc.
Okay, so let me do this. Let me stop the share. And yeah, I've been writing down. So you guys got to speak up quickly. Thanks, Elise, for mentioning that.
I saw the slides, so I'm not sure what happened.
Yeah, me too. I saw your writing.
Oh, you did? So can
Yeah.
you see it again now?
Mm-hmm.
Yeah.
Thanks. Okay.
Oh, so
thanks.
it must be on my end.
Well, I know that that's happened because I talked to somebody yesterday, and it was the same issue occurred. So thanks. If anybody has any issues, do you see it now, Elise?
The screen is black right now,
Huh.
but I imagine that's probably me.
Okay. Other people okay? Other people see it? So it should be recording. So maybe you can go back and look to later on. Where I left off was, you know, whether we have an outcome that may not be normal, but we're going to use a method to transform that into something that's approximately normal so that we can employ linear mixed models. And that's the method that we're learning today. Okay, so GzLMM can be fit by what we call linearizing the data and employing linear mixed models. So I'm going to define pseudo data, okay, and that's why we call it pseudo likelihood. The pseudo data P is a transformation of our original outcome, and then we're going to be able to use linear mixed models to fit that. But the problem is, like a lot of these non-normal methods, you have to use an iterative process to, you don't just do it in one shot, you have to do it iteratively in order to actually get the estimates. Get the pseudo data and also get the estimates for the model parameters. So it's a very complex process. We already know in linear mixed models, we have to use an iterative process to get the estimates, right? We have to use you know, when we maximize the likelihood, that's, we use some algorithm that's iterative for that solution. And now we have to iterate that process when we do this linearization approach, which I'll kind of walk through more specifically as we go forward. So in a nutshell, it's a complicated algorithm. So the benefit is that we can take advantage of what standard linear mixed model theory has to offer. So we can include random effects, and we can also specify error covariance structures. Even though, you know, we talked about before how the generalized linear mixed model in the model that we've defined, we don't have an error term, but this particular algorithm actually allows us to adjust for both for random effects and for specific error covariance structures. So yeah.
Just to double check, did we say like the methods we learned about on Monday can't fit the R matrices?
Yes.
Okay.
Yeah,
Cool.
so that is one of the limitations of the second approach, that we can add random effects, but we can't model the R structure. And so that's what we're seeking right now. We're seeking a way to do that using a different method. So for GEE, we could add a repeated statement, but not random statements. And for the second approach, we could add random effects, but we couldn't add a repeated statement, right? So both the approach 1 and approach 2 were limited in how we can handle longitudinal data. Now we're going to be able to do both. So there is one comment here that this approach, you know, has, through simulation, there's certain conditions where it's shown to not work as well. But those are, you know, for smaller data sets, for particular outcomes like binary outcomes, it may not work as well. So you just have to be careful when you have smaller sample sizes, and maybe you have a 0 heavy or 1 heavy, you know, binary outcome or something like that. I have done my own simulations, and I've seen how this works in comparison to GEE. And like for sufficient sample sizes, they're actually going to be pretty close if you have apples to apples comparisons. Just a bit of history. The papers that came out to develop these methods were, they came out in the early 90s. There were a couple papers that right about the same time that, you know, talked about the same methodological approach. The Breslow and Clayton, they called their methods quasi-likelihood, penalized quasi-likelihood. And Wolfinger and O'Connell, they call it pseudo-likelihood, which I like better because we already have quasi-likelihood. We've used that term quasi-likelihood for GEE models and things like that. So we want to use a different term. And so that's why in this case, I'm going to keep, you know, we're going to keep that terminology, pseudo-likelihood. So how does it work? Are you guys familiar with the Taylor series expansion? Like if you've had math courses, you probably talked about a Taylor series expansion, and it's a mathematical way to approximate quantities. And I'm not going to get into the math of it too much, but basically the idea we'll get to in a second. You do a first order Taylor series expansion. I think it's on the next slide, but I'm going to stay in order here. So a practical consideration, you can do this linearization approach or pseudo likelihood approach using proc-limix, and instead of doing quadrature, instead of saying method equals quad, you would say method equals, and then use one of these 4 acronyms. And the PL is stands for pseudo likelihood. The 2 letters in front of it, the first letter indicates whether you're doing regular maximum likelihood estimation or restricted or residual. So this is ML versus Remel. And then the second letter indicates whether you're doing subject specific or population average type of expansion for the Taylor series. And we're going to talk more, I think actually next week we talk about subject specific versus population average effects. So that may become more clear what I'm talking about, but you can think of effects as being able to interpret effects on a subject basis or on a population average basis. And so depending on how you do your expansion for your Taylor series, you'll have one of those 2 types of effects. So again, we'll talk more about details of that, but epidemiologists, a lot of times are interested in the population average effect, and everyone else is interested in subject specific probably. You can still get average effects, you know, when you have subject specific, but we'll talk more about that next time. So the actual default method, if you don't say method equals anything, we know that there's always defaults. This is true for SAS and R. there's defaults. In proc-limix, if you don't say anything, the default method is RSPL. So that would be using a REML type approach, and it would be using subject specific, approach, and pseudo likelihood. So if you don't say anything, you're not going to do quadrature. You're actually going to do pseudo likelihood estimation. It's going to be a REML type of approach, which would probably get you better estimates of your covariance parameters. And the effects are going to have subject specific interpretations. Okay. So like a lot of these methods, we need starting values, and we're going to use an iterative process. So if no specification is made, the starting values are going to be your basic naive generalized linear model estimates, and that, so you don't really, I don't think it's important here to specify other starting values, because you have ones, you're not starting at 1, which I think is could be pretty off. You're starting from a reasonable intuitive starting point, which are what the estimates would be if you ignored the correlation and you just did a regular generalized linear model. So here is the slide that gives you a little more detail on the Taylor series expansion. So we take the generalized linear mixed model and we consider the mean of that model. And if we do a first order Taylor series expansion of mu about current values, call it beta tilde and b tilde. So those are the fixed effects and the random effects. We get this expression based on the Taylor series expansion. And we see a quantity that involves what we can call our estimates, what we can call our parameters in our model, and our mean. So we can rewrite that. If we rewrite that Taylor series expansion, we can get a quantity where on the right side we have the mean of a linear mixed model conditioning on the random effects. So if we take this left side and we think about the left side is the expected value of this quantity here, conditional on B, and we know that that's equal to x beta plus ZB, then this quantity on the left would be a good candidate to be the pseudo data, right? Because if its expected value is going to be x beta plus ZB, that would be a good good candidate for pseudo data. And that, I don't know exactly why, I don't have the detail here why that's approximately normal, but that this will give us something that has it's approximately normal, or at least more so than like a binary outcome obviously isn't normal, right? But this gives us something, because we did the Taylor series expansion, this distribution will be more continuous and it could be modeled more easily with the normal theory type of model. Okay, so we have, our G is our link function for our generalized linear mixed model. Eta is the linear predictor. Mu is the mean of Y, given the random effects. And so for a particular type of outcome, we can express what that would be. And we're going to do that for count models. So I'm going to show you how to do that. But so the prime, G prime would be the derivative. So you can take whatever G of mu is, and then if you take the derivative, you can substitute that in, and so we can write this out specifically for specific types of outcomes. So a little more detail, the variances here are going to be approximately normal, and they're going to have, they can be expressed this way. So just to back up real quickly, I think I talk about, yeah. So up here, back to the, our defined generalized linear mixed model. What do we know about different outcomes and the mean and the variance? We know that they're often related, right? So for example, the Poisson, the variance is equal to the mean, right? There's an expression that we can write between the mean and the variance. For the normal, it worked out that they could be separate. They're independent of each other. But for other types of outcomes, we know there's a relationship between the mean and the variance. So the variance of y given b, we know that we can write that this way. For a normal, the a's would drop out, right? But what would a be for a Poisson? I hit it so you couldn't read the next bullet point. So let's see if you're paying attention.
Would it just be 1?
It would be 1 for the normal. But what about for the Poisson? So you can think of the relationship between the mean and the variance, right? And you're going to have something, you're going to have an A matrix, and down the diagonal, you're going to put in what that relationship is. So you express something, whatever the variance is, in terms of the mean. Anybody else have a guess? Yeah, I think I heard that. It's going to be the mean. So you're going to put mu down the diagonal, because that you want to put in what the variance is in terms of the relationship to the mean. It's the same, right? So you put in the mean value down the diagonal on A. So going back to this, so for pseudo data, yeah, go ahead. Somebody was gonna.
Yeah, so yeah, in the previous slides from Gary, where it was said in reality, most of the times the variance and not the mean are not equal. So in this case, are we just saying we're using mean always, or what are we implying here?
We're implying, that's a great question, Benjamin. So we're implying that that the mean and the variance are the same under the model, but we will have ways to adjust for over or under dispersion using the methods that we're going to talk about today. So you're right. We are making kind of a model assumption that the mean and the variance are the same, but we will have a way to adjust for over or under dispersion, and that's very important, right? Because we saw last time how if you force it to be a Poisson, and if you have under dispersion, what's going to happen to the standard errors if you don't account for it?
Okay.
This is for anybody. If you don't account for under dispersion, what's going to happen to the standard errors? Think about what we had to do to get a closer standard error. What do we have to do in those processes that we talked about? I think last time and maybe even the time before that with GE.
I think you'll get too big of standard errors if you don't account for under dispersion.
That's right. That's right. Because what we did was we multiplied by the square root of the dispersion parameter, right? And so if there's under dispersion, it's going to make the standard error smaller. So if we don't do that, the standard errors are going to be too big. And it's flipped around. If you have over dispersion, then you're going to underestimate the standard errors, because you would have to, you know, multiply by something bigger than 1 in order to get the right thing, right? So we'll be able to do that, and I'll talk about how that's done. So this is just a description of how the variance of the pseudo data is in relation to the variance of original data, and then how we can use we could use a weight statement in linear mixed model to get the appropriate variance of the pseudo data. So if we're specifically talking about Poisson, the A matrix has the mean elements down the diagonal. G prime of mu is going to have 1 over mu, and it's just doing basic derivatives here. So we can get an expression of what G prime mu is for a Poisson, and we can figure out what the correct weight is going to be so that we can get the right variances and the right right model for this type of outcome. So this is important. So as the linear mixed model for the pseudo data has parameters and random effects that are of interest in the regular generalized linear mixed model as well, we can essentially conduct inference for our fixed effects and random effects using standard linear mixed model methods, using converged values in the model for the pseudo data. Okay, so there's a few more points there. I'm going to go to the application to kind of demonstrate how this works. So we're going to look at
I have a quick question, Matt.
Yeah.
Can you always linearize the data?
Well, you do the linearization based on the type of distribution that you have, right? So if you have a binary outcome, we can develop the methods, the linearization methods for that type of outcome. For a binary outcome, for a count outcome, we can set up the model in that way. And what I'm going to do here is I'm going to show you if you have a count outcome, and we assume like the Poisson model, this algorithm can be specified for that. Now, how well does it work for a certain type of data? That's the question. It may work better for some type of data than others. And for example, like I mentioned before, like if you have a very small data set and maybe you have 0 heavy or 1 heavy binary outcome, something like that, maybe it won't work as well. Mm-hmm. So it's true that maybe for certain data, it's not going to work as well, but we can always set it up for the specific type of outcome. We can kind of tailor the methods to, you know, to a binary outcome or to a count outcome.
You can't always linearize so your pseudo data is not always going to be normal, depending on your original data.
I think it may vary. That's kind of a good question. That, you know, I have looked at the distribution of the linearized data, and I haven't done that for a ton of data sets, but I've done it for some data sets. And it's not exactly normal. I mean, it's not perfect, but the most important thing that we want to see is not that the P is normally distributed. We want the parameter estimates in the model to behave well, right? We want our estimate.
If your P isn't normal, then your parameter estimates don't converge to the proper parameter, right? You're
That's not necessarily true. That's kind of the point I was trying to make, is that, you know, that it could be maybe approximately normal, and it may still work perfectly fine.
okay.
So you can't tell by just looking at the distribution of your pseudo data whether or not this method works. I don't think that.
Your first beta tilde, that affects your convergence, correct?
So I'm going back to, I'll go back to the,
Because you start from there and then you do a Taylor expansion and then you reiterate. If I understand this correctly.
it's based, this Taylor series expansion just gives us an expression for the relationship. And so we use this expression to figure out, you know, ultimately what the relationship is between the original data and this new pseudo data. That's the model that we use based on the Taylor series expansion.
Okay.
But
then
yes,
your reiteration is based on the beta tilde and the b tilde, correct?
Yeah. So
you have outliers in your data set. You're converging towards the outlier, right? If you're skewed, is that not right?
Well, that we can talk more about that. You're bringing up a really good point, that there could be data sets where you could be thrown off.
Okay.
And sometimes, you know, like the models we're starting to look at now, we realize that they don't always converge, right? Sometimes we just don't get convergence. And so the general point you're making is an important one, that this will not always necessarily work. But I would also say that you can't tell whether the method is going to work just by looking at the distribution of the pseudo data. It may still converge to the right thing.
Okay.
As I go forward, I'm hoping that, you know, that I'll be able to look at more examples, you know, of different types of data. You know, with the application I'm going to talk about here shortly, I did look at the distribution of the pseudo data, and it wasn't a perfect normal distribution, but it was much closer than than using Y, right? Use the distribution for that is much more non-normal. So this is the example that I'm going to use here, and this is data that I presented before. We're considering albuterol use. So the kids are using a rescue inhaler, and they use it when they don't feel well. So it's a symptoms type of outcome that we're considering. And this particular data, I actually spent a lot of time on this because I was interested in initially air pollution models to see, are they going to use a rescue inhaler when there's more outdoor air pollution? And that's what we call this ambient PM 2.5. So this is essentially outdoor air pollution. And PM 2.5 is essentially going to be fine particulate matter. So these are solid particles, but they're suspended in the air. In the air. And then the other one, cigarette smoke. There's different things that come out, you know, when you smoke. One of them is particulate as well. So we have PM 2.5 due to cigarette smoke. So these kids, you know, they have asthma. So there's a concern that, you know, if they're exposed to outdoor air pollution, and even more so, what if they're exposed to cigarette smoke? Maybe their parents smoke. And so So again, this is the fine particulate. So you could have these particles in the air that are caused by, things like cars and industries, that, outdoor air pollution. There's that source, and then there's also the cigarette smoke. But the big question for me was, how do they interact with each other? If you have more exposure to one, how does that affect the relationship with the other one to the outcome? So in order to do this, I had to include both types of air pollution as predictors in the model, plus their interaction, to see what was happening with all of these things at the same time. And we have a count outcome. I'm going to use the Poisson approach. So we set the model up where the mean and the variance are the same, which we know that that's not necessarily a great approach, but again, we'll be able to account for over or under dispersion. Now, if you take that definition for the pseudo data and you write it out for the log link, for count outcomes, you specifically get this transformation for the pseudo data. So this is specifically for the log link. So it tells you that you take your original data minus your mean estimate, and you divide by the mean estimate. So it's kind of like a type of standardized value that you get, and you add the log of the estimated mean. Then that is the transformation using the Taylor series expansion that will give us the pseudo data. Okay, so in our process, it's iterative. We get initial values in step one, and we get these initial predicted values for the model. We create the pseudo data based on this log link, and then we fit that pseudo data in a linear mixed model, and we get new values of our pseudo data and the weights, which is going to be important for the variance. We obtain new predicted values, mu tilde, and then we go back and fit the linear mixed model, and we do that iteratively until the solution converges. And it usually does. So Jonathan was saying, well, what if you have extreme values? And maybe, yeah, sometimes it doesn't converge. And then what do you do in that case? Well, you can, maybe modify your model. You can look at your data to see what's happening. But in a lot of cases, it will converge, and you get an estimate. And then we have then a way of estimating parameters in the generalized linear mixed model. But now we can use whatever linear mixed models has to offer. So we're not restricted to just adding random effects in the model. There's some technical notes here. If you have zeros, the problem with zeros is that then you're going to have zero weights. And so one adjustment you can make is if you add 1 to everything, as long as you're consistently doing it to all the values, then you're not going to lose values because of having 0 weights. So this is kind of a technical note. You can see that when you get your estimates at the end, they should still work fine. And a few other technical notes that'll let you guys read in more detail. So we can use proc limits to do this, but because of the fact that for the data that I had, I wanted to see how Glimics actually worked. I wanted to actually do it myself. And there were real reasons that I had to do this, because I can explain that later, but I basically wanted to write more from scratch this algorithm. So I wanted to use proc mixed iteratively to see if I got the same solution that Glimics got. And so the code that I have here is SAS code. This first part here is the initial fit. This is just step 1, where you get the initial values, and then you get your pseudo data. And then this is the iterative part where we're repeating steps 3 and 4. What was step 2 again? I forget that. So actually step 1 and step 2 are shown up here, where you fit the model and you get your pseudo data. So steps 1 and steps 2. And then these are steps 3 and 4. And this is iterative. And I did this kind of, I probably could find a little better code to do this. I put it in a macro, and then I did it until I got convergence. It took me 7 iterations for these data. So iteratively, I use mixed to fit the estimates, and then I use those estimates to recompute the pseudo data, and I do that iteratively until convergence. And I was pretty happy with myself. It took me a while to get this, but I was happy because I know I have a better understanding of proc mixed, right? And I want to understand, instead of having this be kind of a black box thing, it helped me understand this approach a little bit better. Now, you'll notice in the proc mix code, I have a random intercept for subjects, and I have a repeated statement, and I have the spatial power. Why am I using that? Because the data may not be equally spaced. There could be days where we don't have data collection. And so this is what is really the underlying type of structure that I'm using here when I use the spatial power.
A more flexible AR1.
Yeah. So yeah, it's an AR1, but it's like a continuous time AR1, and will allow for unequal spacing. That's right. And so again, not only can I just use AR1, I can actually use anything that mixed has. And so if I have intermittent data, I can incorporate that into the process.
So are you using REML for each proc mixed iteration?
I am. How do we know that I am?
Because you're not specifying anything else.
Exactly, because REML is the default, right? And depending on how I did the expansion of the Taylor series, I'm either doing the subject specific or the population average, but I think I'm doing the subject specific approach based on the expansion that I did. I'll double check that one.
Can I ask a next question?
Yes.
On the repeated statement, is it specific to the spatial power that you put the variable date afterwards compared to in front of the backslash?
Yeah, so
repeated date backslash.
So that's a good question. You know, a lot of times you put a variable after repeated to indicate what you're taking the repeated measures on. As long as the data are sorted, and this, I would always do this, sort the data by subject and then by date. And if you do that, you don't need to put anything after the repeated. You could put date in there to indicate you're taking repeated measures on date. That's our time variable. But as long as the data are sorted correctly, you don't need to add that. And that's true for, you know, in general. So we have, you know, our predictors of interest in the model statement. We have our random intercept. We have the repeated. So now we're accounting for the serial correlation, and we're doing this iterative process. You could do the same thing this way. It's a lot more succinct because proc limits, you know, it's our canned procedure that will do this for us. And the coding looks a little bit different here. The main thing that looks different is this statement right here. What is that? I still don't know why they do this, but this is essentially our repeated statement. Instead of using an actual repeated statement, we use a random and then we put underscore residual underscore as the argument. This is essentially our repeated statement. It just has a different look to it when we do proc Linux. I kind of wish that they would just, use an alias here. I don't know why they do this, but it is what it is. So the other thing is, I actually use a spatial exponential here. I think I may have had trouble in convergence using spatial power. It's just a different parameterization approach, but should get us estimates for the fixed effects that are the same, as long as the convergence works for that. And what I did here, I actually used MSPL in this code that I have. The reason why I did that is because I'm going to want to compare to the quadrature approach to see how the results compare to each other. And quadrature is based on the standard likelihood. One thing that you'll notice is I have a pconverge or pconv argument here. And that is because I had trouble with the criteria of convergence. It didn't work with the regular convergence, so I softened it just a little bit. And obviously you have to be careful when you do that, because then you may get convergence to not the correct estimates. But I softened it just by, I think, by a magnitude of 10. So I moved the decimal place one over to get convergence here. And occasionally you may have to play around with the convergence criteria to get things to work. But again, I would be very cautious about doing that. So in our output, I think we're on track to finish here, but I'm gonna essentially just get through the results here and talk about the estimates. So when you look at the output, you'll see the fit statistics, and we know that the generalized chi-squared divided by degrees of freedom, what does that tell us? That's an indicator of over or under dispersion in our data. And so when you look at that, you might think that we have a problem here, right? There's under dispersion. But the thing is, when we add the error term in the mixed model, that has that specifies the spatial approach, which is essentially continuous AR1, and we also have the residual variance. That residual variance is actually going to be that amount of over or under dispersion, and is automatically going to correct for over or under dispersion. So when we add that, I'll call it R side effects in our model, in other words, the error covariance structure in this approach, by doing that, we're automatically adjusting for over or under dispersion. And so it'll work, in this case, we know that this rescue inhaler use tends to be under dispersed, and we can see that by this estimate. And so our estimates below, our beta estimates and the standard errors in particular are going to be adjusted appropriately. Okay, so that's one of the good things about this approach. We didn't have that when we did that quadrature. If we fit this Poisson model, we didn't have the ability, using that standard likelihood, we didn't have a way of adjusting for over or under dispersion. So this gives us an advantage when we compare it to quadrature. specifically for this, this type of outcome and using the log link. So we look at our estimates. We have estimates for, Friday temperature, the study year. These are the values that I'm really interested in. So these are W1 is the cigarette smoke exposure, and W2 is the ambient pollution exposure. So this is saying that, and we have an interaction here. So how would you interpret this one, 2.29? It's positive, right? And we know the outcome is rescue inhaler use. So this would be saying, this would be the estimate of the relationship between cigarette smoke exposure and rescue inhaler use, specifically at what? In the absence of ambient, right? Because we have these two and we have an interaction between them. And similarly, this 1.63 would be the pollutant, the ambient pollutant effect in the absence of cigarette smoke exposure. And what does the interaction tell us? It's negative. No, there's a fair amount to digest here. So this is our outcome. This is inhaler use. And this is pollutant level. So when you can think of it conditioning on one or the other one, but let's say we're conditioning on cigarette smoke exposure. So if there's no cigarette smoke exposure, there's some slope relationship, right? At least on the log scale. This actually be on log scale. It's log linear. So this would be for no cigarette smoke exposure. What would happen though to that relationship as we increase the cigarette smoke exposure based on the estimates that you see there?
The slope would go down.
Yes, good. So the slope would go down. So let's say we could say want to be able to let me be picky here because I want to be able to do 3 of them. So there's none, some, cigarette smoke exposure, and then as it increases, that slope's going to keep going down, right? So it's going to be, so for higher cigarette smoke exposure, which seems weird, but basically I think what's happening is if the kids are already exposed to some type of exposure, that they're getting from around their house, maybe they don't react as much to the air pollution outdoors. Whereas if they didn't have smoke exposure, if they didn't have smoke exposure, then they don't react as much, or they do, sorry, they do. I'm getting myself backwards here. So there's a negative interaction that impacts their ability to respond. Now you might think, well, that would make cigarette smoke seem good, right? Well, maybe it weakens their allergic response. That's important, for one thing. The other thing is, I may not have drawn these lines. These actually, I'm going to go back just to move these a little bit.
A quick question, Matt. Don't you have to fit the model without the interaction to make interpretations on your main effect?
No, I would say you wouldn't have to do that.
Okay.
But you do have to be careful about how you interpret the main effects. I'm gonna redraw these. So it's actually, it's probably a little more like this. So this would be the sum, and this would be the high. So it's not like you're using less inhaler use necessarily, but the slope relationship is being modified by pre-exposures to something else. Okay, so it's pretty complicated, and we're trying to understand the biology of what's happening. But to Jonathan's point, like so what we can do with this model, we can see how a relationship between one variable and an outcome is modified by another one because we have the interaction in there. But I would say that you can get everything you need out of this model. You don't have to refit a model just with main effects in it. It's just being careful about how to interpret the effects that you have. One of the issues with this, and I know we're out of time, so I'll wrap this up real quickly, but we're using predicted values in these models. And because of that, really you need to account for the variability in the fact that you use predicted values and not actual observed values for your predictors. And so I did that in my research, and we'll talk about more about measurement error methods and how to account for that type of variability. I will do that later. The next slides essentially show you, comparisons of using GEE versus the quadrature approach to generalized linear mixed models to this new method that we have to account for both random effects, to distinguish subjects and serial correlation at the same time. And I think what I'll do is, again, I'll probably just take 5 or 10 minutes at the beginning of the next lecture to recap this. But essentially, today what we learned is a new methodological approach to fit a generalized linear mixed model that's more flexible than the previous models that approaches that we had to doing that. I'll post a homework here shortly, like within a day or two, and hope to see interesting stuff about your projects here by the end of the week. Is anybody interested in talking for office hours? I know we don't really have a specific homework right now, but was anybody going to hang around for office hours to talk? If not, that's fine, because I do have a bunch of stuff to get done. If you have specific questions you want to talk with me with, I've already talked to a couple people about their projects, and we can set up a time to do that individually if you like.
Are you going to make an assignment on Canvas for us to turn our thing in by Friday, or do you want us to email you them?
Oh, I didn't actually put the link up. Obviously I didn't. So I will do that. I will put a link up. Yeah, I'd like to just have you do everything on Canvas. So thanks for the reminder. And again, you don't need anything really fancy. I just want your project. What are you going to do? Basic research questions, and whatever else I ask, but it doesn't have to be too fancy at this point. Okay. All right. So thanks everybody. Have a good weekend. Just send me an email if you'd like to talk further. I'll probably show up just for a minute or two at the beginning of office hours, but if no one comes, that's totally fine. And you'll probably have a couple weeks to get the next homework done. Okay, thanks everybody. See ya.